go.
So it's an honor for us to have Hartmut Neven here from Google. So Hartmut got his PhD from Ruhr University in Germany. He later went on to University of Southern California as a professor and later as the head of the laboratory for human-machine interaction. And after founding two companies that apply computer vision to real-world applications, he now is at Google's Santa Monica office, where he leads the efforts in Google Goggles, which I think you all know is Google's visual search engine. So in some way, he's sort of an ambassador for this whole field to the rest of the world. So I think he will tell us a little bit more about what's going on behind Google Goggles. So please join me in welcoming you.
So, okay. Since I've given a lot of talks recently about Google Goggles, I have some feelings that most here in the audience will have heard or seen things about it. So I was thinking, rather than going one more time over sort of the well-documented wins or things that work well, I thought to rather give you a view into the sausage factory and show you areas where we are struggling with right now. So those are not necessarily that well documented in terms of academic standards, how do we compare to every other method in the literature, but you get a feel of what are the areas we are working on. And even though we are a pretty large team, I want to call out three people whose work in particular I will talk about is James Philbin, Pillai, and Rabinovic, and I will mention this when I get to their specific pieces. So I say I will quickly go over the latest additions we did to Google Goggles, and then two areas selected out of many we're working on. One is how we can scale dynamic index object recognition to about 1 billion objects. And the key word here is dynamic. We want to be able to, while queries are going on, we want to add new entries into the index. And then the second area is the recognition of weakly textured objects. So those objects that make problems for us today, and Goggles is not ready for prime time. So what is Google Goggles? And I hope that most of you had a chance to play with it. It is these were born as a mobile visual search application, so the notion is you submit an image rather than a text query, and then you get information back about the object depicted in the image. And so what can Goggles recognize? And recognize all sorts of things. So this was an event for advertisers in London to give them a sense. So it's a laundry list of stuff. So it's artwork, it's famous buildings, it's street scenes or matches against street view, I should rather say, logos, packaged products, watches, electronic goods, text, or various languages, barcodes, on and on. But of course, many things we cannot yet recognize, and those are the more interesting ones. Here, just going through some recent feature additions. So just a few days ago, we brought the Goggles 1.5 version out, and that before we had the ability to read OCR in photos, Latin characters, but now we are also able to read Cyrillic letters. Also, we want to expand, eventually capture other fonts and alphabets as well. And of course, it's, to do this is particularly interesting when you tie it to another big investment Google is doing in translation. So you can not only OCR it, but translate it. And then we also improved address block reading, so scanning a business card or any address block. So the notion is that in the future I never want to have to say, punch in the numbers of a phone number I see somewhere, be it on a desktop or be it somebody has scribbled it down for me. I just want my phone to read it. So just here it is, make a call to that number, send an email to that address. Another piece, maybe boring here for the audience, but very important from a commercial perspective, is fast local barcode reading, because that is one of the number one visual search use cases. People, when they are in the supermarket and they buy a video game for their son, they want to have a rough idea of what I'm paying here, should I rather get it on Amazon? So barcode reading should work well, and this was important enough for us to not just have it server based, for pretty much all goggle recognition disciplines, but barcode reading we brought it locally. And then of course, also want to have some fun. We put, just for the heck of it, the Sudoku solver goggles. I felt it has worked like a charm. This was just it's a parlor trick, of course. You can argue and used to it. But we wanted that people show it around, saying what this application can do. And I think it also drives home for the average person a little bit what AI or computer vision really is. I think to many people not in our field, that's a bit amazing, as a piece of a sheet with a game you're trying to solve, and then you swipe your phone over it, and then it solves it for you. Because several things have to be combined. You have to first know it's a Sudoku, and of course you have to be able to read the digits correctly, and then of course it has to be a little bit of a game engine to solve it for you. Another addition is, again, not so amazing from a computer vision perspective, but we have now feeds for the main magazines and newspapers in the US. So if you try it out, pretty much any ad in magazine that you're going to find, you will be able to recognize. We also just recently in a commercial with HTC for a new Android phone, we have brought goggles to TV so that you can recognize off TV ads, which of course we refer to these use cases as media bridging. And there's of course interesting, there's a revenue potential there to link a brand marketeer. But there's just value to it if you have a brand, you take a picture of it, and to get to special results, you almost have to caress the brand. You can sort of tap on those bounding boxes, so to link a Starbucks logo to a special Starbucks sign. That is an attractive use case. Then to finish out with two more pieces. Goggles is available on the iPhone. It's a little bit behind in the feature, which is behind the Android version, surprisingly. And you may have seen the goggles stack, these large parts of it are now also accessible as a desktop. So image search has a little camera icon now where you can do a search language. And then a non-vision related feature, but important, is we allow now for user annotations. So people can, for themselves or for goggles, put in metadata to images for their own consumption, like, well, this is a nice gift for my niece, or they can add to the goggles index. And this can hand in hand with a better search history that also lets you find where those pictures came from on a map. So this would, for example, be a nice set of tools in collaboration with Peter if, let's say, we wanted to entice more people to contribute images of leaves and plants, and then we can not only collect it very conveniently in this way, but it's mapped in the proper way. We have the time and the geolocation stamps and know where the data came from. This is a sort of my humble attempt at taxonomy of all things, because goggles is universal search, or has the ambition to do universal search, which means we want to recognize any object of the planet. I don't want to be called by a philosopher what exactly I mean by this, came more sort of with an engineering mindset to it, and we just broke down the bag of relevant things into basically divided by character recognition engines. And here this graph shows a little bit what is possible in the green areas and what is not yet possible in the red areas. And that maybe should also say that Goggles has this architecture. It is not the one-size-fits-all vision algorithm. I think that the field started out, or it's probably also going through fashions. There were hopes that one strong vision algorithm would be able to eventually be applicable to any visual recognition task. That hasn't turned out to be the case yet, and of course also for the human brain, the theory that the human brain is a bag of tricks is still a valid non-defeated hypothesis. So going here through a few areas. So OCR, again, very important as a use case for Goggles. A little bit overlooked by academia as a challenge to recognize reliably text and photos. Only the best engines, and I will say something about this in a second, the best engines we found when we started this were on 20% word level accuracy for text and photos, which is of course not good enough for a commercial product. And, this has not only to do, but of course this is compounded by unusual fonts. And logos, well-textured logos, we can do pretty well. Starbucks logos, very simple logos like a Nike swoosh are very difficult for us. Why? Because if you do universal search, you need to then, in this pattern per se is everywhere. If you look into a tree, you will find little swooshes like this everywhere. And it's essentially our blending with scene understanding, or scene analysis that we understand, or when I look at a forest picture or I look at a place with trees. So I'm not inclined to bring up logos or Nike shoes. But we don't have this ability yet, therefore these very simple shapes are difficult for us. And products, again, textured ones at the back with high reliability. Those that have little texture, such as designer chairs in cars, those are still challenging, and those are, we loosely define weakly, or those as weakly textured objects, which is defined as objects where interest-based, interest point-based methods don't really work well. And those get a lot of attention these days. We really would like to be able to recognize those. Places, Goggles has a couple of 100,000 famous landmarks around the planet, and it does matching against street view panoramas. So things like Taj Mahal can be recognized very reliably. Faces, we've made nice progress. We are approaching sort of the take a picture and match against mankind. But unfortunately, that's the forbidden fruit. The privacy challenges are just too large. We won't offer it. The politically correct statement is until such time that we figure out what good privacy models are. But at this point, I'm getting less optimistic we will find those easily. Plants and animals, we've heard about this today quite a bit. We would love to be able to recognize this better. We can't yet. Barcodes, but the green sector, and maybe I stop here, or I should maybe say that Goggles has also these catch basin engines. One of them is, in my taste, the most amazing one, called the Toto channel. It stands for the other textured objects. It's essentially the things that I haven't explicitly called out yet. Because the idea is simply we can do textured objects well. So why not go into image search index, grab everything out that is textured, which can be wall clocks to some paintings to all sorts of stuff. And I always amuse myself with what Goggles knows already, and many people don't try this. Let's say I rented a car here and a Toyota Camry, I think, took a this is other textual objects, essentially prominent images crawled or taken out of the image search corpus. So the design principles behind goggles are, you want to do universal search, full well knowing that you aren't wild areas, which sort of constitutes therefore a moment of truth for computer vision, because you sort of wake up frustrated with all the things that you cannot recognize well yet. Trying to do this makes it, of course, much harder than trying to serve a particular vertical. If I only have a barcode reader, only do a wine spectator type app, I can play all these special tricks. Many false positives will never occur. But for universal search, you have to deal with this, which has direct design implications. We need really low false positive rates, which excludes a lot of the methods that are described in the literature. Then, this is about fine-grained categorization, but goggles initially really is after instance recognition. It's not good enough if, let's say, you see a designer chair and you think, oh, this would look chic at my house and I would like to have it and to take a picture of it. If the answer is back in a chair, or even designer chair, that's not good enough as a label. What you want to hear is, okay, you can buy it at IKEA at that price, and there's a coupon for it available. So the more specifics, the more value the user will get. Another thing we need to do is, on a phone, if people don't have much time, there's also not much leisurely browsing going on. So we need to put our best foot forward. So we only show 3 results. And it better be in those first 3 results. And also we don't want to bother, that would make our lives much easier if we could ask the user to select modes. It goes a little bit what I said earlier about universal search. We can have the user help us a little bit. Of course, this will go a long way. For example, the user says handbags while taking a picture of a handbag, then we only crawl the handbag with corpus, and of course the results will be much better. And eventually we will phase these things in, but initially we saw this will not scale well, because then also it's bad discipline for the engineers. The person working on the code was saying, oh, why don't we just help the system by giving some game-related information, or people refining beverage or wine recognition. There's just the temptation is too large to ask the user to jump through too many hoops. So we decided let's do an AI style and we'll be trying to find those things automatically. Then, of course, our final goal, and I think that's reachable. I have the sense that in about 10 years, again, don't want to have a philosophical discussion on this, but sort of roughly speaking, I feel that in 10 years, 90% of the things we're interested in, we will be able to recognize. And we can see a little companion looking over your shoulder, and it's conceivable that this companion will know more about the world than any one of us. I mean, the pivotal moment for me was when we turned on the art corpus. At the time I was with the New York goggles team, and I also on the weekends I went through museums, and so overnight, suddenly goggles knew a few 100,000 works of art. So how many does each one of us know? So it's very conceivable that we have a system that looks over your shoulder, and in principle, and all privacy concerns aside, could know who everybody in the room is, can read every piece of text, regardless in which country you are, would know, basically any interesting object in your field of view. And that's the goal. 10 years, I was told 10 years predictions are the hardest and nobody likes to make. Because 1-2 years, everybody sort of has a good feeling. 20 years, 30 years, you are easy, because nobody will recall it. 10 years is sort of tricky. So quickly some statistics. So I think you really have the bragging rights that this is the largest computer vision system ever built, in the sense that the databases behind goggles, several million images. And here is sort of the good news, bad news piece. Where goggles is installed on those phones, we see that the visual search cures, visual search as a complement to include text search, voice search, constitutes about 1% of all search queries. So you can be frustrated about it, or that's not bad. Google level traffic, 1% you add, that is in some ways a success. In some ways, because it doesn't target these 1%, were those really useful, did we deliver good value to the user? When we increase the number of 50% of the queries, we are now able to give a specific result back. And one important thought I always have about visual search is that I distinguish between externally and internally triggered searches. So when I sit tonight in my hotel room and I think, oh, I deserve a nice summer vacation, and then I can put hotel in Rio de Janeiro in as a text search, just born out of an urge from within my brain, versus, so that's internally triggered search, versus something like Google Goggles or Shazam on the audio side. They respond to external triggers. So you stumble over an object that you find interesting, and you take a picture of this, and then you learn more. Whereas many of us are in environments that know pretty well already, so the opportunity is, there's just less opportunity for visual search. And accordingly, we also see more usage when people travel. So in Paris, there's stuff for you to do. In artworks, buildings, translating the menu, there's more stuff for Goggles to do than if you're sitting down. So before I get to the two areas, we will cover a brief update. Some of you in the audience are interested about this. So we have been kept kicking the ball forward on face recognition, and we are now working on experiments which go 1 against a billion. And so here, these are the latest results we have. It's the figure on the right is sort of the mouse. Go here. And it's the most amazing to me. So this was 500 million, this specific test. And it shows you the median rank for the first correct result. So the idea would be, I take a picture, and then I have a ranking, most similar, second most similar, and so on. And then where does the first correct one show up as a function of samples that are in, so how many times am I in the album, so to speak. And here sort of is the interesting number. You are within the first 10 with 50% probability if you have about 16, 17 pictures on the internet. So at that point, so if I'm really interested in finding you, you would probably show up in the first 10. And if you want to be in the first place, this is rank 1 probability. So really nail one, so take a picture of Erwin and Helen. Then you would have to do this with 50% probability. That's a bit harder. You would need sort of, let's say here, 35 to 40 images on the internet. But that's, for many users, not that many. Many of us have that amount of pictures on the web. Another area where we made nice progress in, I told you about how we call it photo OCRs. So you're reading text and photos. And I feel it's a little bit an underappreciated area, probably because speculate about this. And sort of engines that we looked at earlier have about that we call a precision characteristic. So you don't get much above 20%. But we have sort of built from scratch, machine learning based photo OCR system. The guys are doing pretty amazing jobs. This has more than doubled the accuracy. But these are just brief glimpses. I'm not going into what's being done there. And now we'll talk about two areas where in object recognition we try to make progress. This I've shown many times. This is our standard sort of this is for the texture object recognition engine. Illustrated here, and it largely follows the systems that many computer vision systems follow. I think first time sort of end-to-end description came from David Lowe. So we do interest point detection, then extract features at every interest point, then do similarity-based matching, nearest neighbor matching, then geometric verification and probabilistic model to do the final decision. But a lot of the details are different. So this is a way how exactly the interest points are detected, and also feature types that deviates a little bit what's typically described in the literature. Also in previous talks, those that heard those, there's a lot of machine learning based filters sitting on top of this engine and making basic decisions such as, hey, this feature is likely to produce false positives, takes this out of the index. There are special systems that deal with self-similarity. So it's a pretty complex system by now, but again, the base system is the interest points, various kinds of simultaneously used interest point detectors. And we stay sort of true to our roots, use Gabor wavelets as the main feature type to describe feature points. We still find those the most versatile features. Then comes the nearest neighbor matching. Quickly, saying, I've also talked about this many times. We gave a slight twist to using Gabor wavelets than the original Gabor jets that Erwin had in his slides and that were pioneered by Christoph von der Malsburg. Essentially what we are doing is, if this is my interest point, then we detect, of course, wavelets of different frequencies or wavelengths and different orientations. And the question arises, how do I do this in an optimal way? And we initially had started out with some pattern, okay, just sort of organize it in a symmetric fashion around the interest point, make sure that you cover frequency space, so these are easy design decisions. And then that's how we started, but we were not sure is this really the right pick, so we did a simple genetic algorithm optimization on it. And normally when you do these optimizations, what you get back, you can't interpret all that well. But here we got lucky. This came back and made immediate sense to us. Because the conundrum is that if you are at an interest point and this guy is, let's say, close to the border, then if you have a big wavelength left, let's say it's here, you want to go after the big wavelength, then you easily fall off the contour of the object. So you optimize this by bringing the biggest wavelengths into the middle and then start from there. So the next big one, you in a compact way put around, but sort of the smaller they get, you can have more small ones than you can have big ones. So if you organize it this way, you get a good compromise between covering all wavelengths, but keeping your feature compact. So those we refer to Congas features. Actually, this has never been published, but there's a patent on it, and of course that's went the wrong way to advertise it. I wanted to say those work way better than pretty much any feature we looked at, including, of course, SIFT. So I would encourage people maybe to look up Congas features and maybe consider using those. They work pretty well. Google is pretty much the standard feature. So, how many minutes left? Okay, so now the two new pieces of work. And this is work by James Philbin and Andrew Sisserman, a student who joined our group, and Anna Pillai, sort of the server Google infrastructure guru who assists James in managing large number of machines that need to be in place for such an index. So we wanted to build a new index to hold images, and the requirements, of course, are high precision. But what I explained earlier is that we want to go to a new phase for goggles. Right now, it's largely curated databases that we have crawled somewhere. We went into Picasa, or we went into Street View images, or we did or to build out, let's say, our art corpus or our landmark corpus. It would really be nice to allow users to submit pictures. So if you want to use this at scale, you need to, and of course the user will only like to do this. Right now actually Goggles allows us to do, but it goes sort of into this black box. We are not committing right now to do anything with your annotation. But that's not what users want to see. If they, let's say, see a movie poster and they say, you know what, you're telling me if I annotate this and the whole world is going to see this, so if I say this movie sucks and the next guy picking up his phone and see my comment, that's great. And I think people will go for this, but only if there's immediate satisfaction. So they need to see their results showing up for Google searches pretty much instantly. So we needed a new dynamic index where you can add new documents within seconds. And of course, the usual thing, you want to do that many images, you want to do it on a single machine, so it has to be easily parallelizable. And of course, if you have a large number of server cats, some always go down, and sort of your system cannot be too fragile when individual servers fail. So the how do we do this? So basically, the piece I'm talking about here is the nearest neighbor engine is replaced. All the other pieces being constant. And we are looking at the dichotomy of full representation versus visual words. And of course, why is this even an issue? So again, we have descriptors of the interest points in feature space, and we want to find in important stage in the object recognition the nearest neighbors for the features of the query image, find the nearest neighbors, or the corresponding neighbors from the database images. And the only reason that is an issue is that ideally you would do it by exhaustive search, but that's just slow, and these on current machines, but we'll see maybe one day there are special hardware architectures for it, and this whole problem goes away. But for now, this is something to deal with. You cannot do exhaustive search, so you have to do approximately nearest neighbor search. There have always been sort of two schools how to go about it. One is full representation, meaning the vectors you extract, you keep in their entirety, or maybe you do a PCA reduction a little bit, but basically it keeps the vectors alone. And we heard earlier arguments why that is important for high precision categorization. And there's no question, anything below this you will lose information, so you can never be as good in accuracy as full representation that this leads to believe we arrived at. But of course, many people have less machine resources available than we happen to have, so it was natural to introduce the idea of visual words. Do I really need to keep every feature, or can I just lump them together and introduce the idea of an alphabet? And how that was typically done, you sort of tessellate, quantize the feature space, and then rather than keeping the full vectors, you only store the ID of the Voronoi cell your feature happens to fall into. So that's your visual word. And what are the pluses and minuses? Full representation definitely will allow for more accurate nearest neighbor finding, but you need minus. It needs less or more memory is a minus. So yeah, vice versa, the visual words have the pro that it needs less memory. And this is maybe not that obvious, but it is easier to upgrade an index when you work with visual words rather than upgrading the tree structure for visual search. Sorry for your nearest neighbor search. So that is how we did it so far. We followed David Lowe's lead there and used the KD tree, but of course already the current indices are above 100 million, so there are a couple hundred million images. You cannot hold this into a single machine, and so you need to parallelize KD tree, and that has always been considered to involves backtracking. And if you have to, say, if you do the obvious parallelization working with root machines that then distribute out to leaf machines, if you have to cross those boundaries, that is not an efficient architecture. But it is doable. The current system relies on a parallelized KD tree. So now this is a new attempt to make this index dynamic. Is we went back and we actually did many tries. We had over many years, we had many interns or students coming in, or our own engineers try to beat the parallelized KD tree in accuracy. We have tries hashes of various types, various approaches to visual words. And each attempt sort of was unsuccessful until very recently where James joined, and since he did his PhD on it from a very good lab, so we thought, okay, James, you get another go at it. Please try to see whether you can do better with visual words than we could do with full representation and KD tree. And he managed to do so, and I don't have the time to go through the details, but I give you the main idea. The main idea is to do a hybrid. You don't fully throw away the information the feature vector contained in each cell, but you introduce Voronoi tessellation, but in each cell you do a product quantization to reduce the information you need to represent each feature. So this gives you sort of the best of both worlds. It allows you, on the one hand, you start to, you can work with visual words, and you can get away with less memory, but you can still do across cells, sort of find your exact nearest neighbor, or almost exact nearest neighbor, by measuring appropriate distances. So there are a few tricks to doing product quantization properly. One is that, I wonder whether I might just skip this piece. So I will just leave it here. So the take-home message for this system is it's a hybrid system that takes ideas from visual word systems, so it does quantization of feature space and works with Voronoi cells, but within each cell, the features are represented in a product quantization manner used for the bitwise embedding. There are a few other tricks to make this work well. So here you see the accuracy of the new engines, adopted the Cyclone engine, and you see in accuracy it comes slightly above what we used to have before with the parallelized KD tree, but to be honest, this tiny difference is not significant. So I would say on the accuracy side, you really don't gain. It's also maybe, I think these things matter, is that the engineer who was responsible for the KD tree implementation, he's not with us anymore, so it's a static system, so since the years this hasn't improved, while James keeps at it. So, you know, this matters, but I would say from a strict analysis, full representation cannot be beat, and James will be the first one to say that. But the interiors, sorry, I should have said, this is on book covers the results, and here's accuracy in landmarks. Now look at the absolute numbers. So this is where you have a lot of negative, no books or no landmarks in the current set. The important thing is only the relative positioning of the RC curves. So in accuracy you don't win, but what you got is it's just much easier to deal with visual words systems from an implementation perspective. So we are able now to go to 1 billion images with those. You save it RAM. No wonder it's a quantized. That's the whole point. It's a quantized representation. So you have 3 to 4 times less RAM than compared to a full representation. The CPU load is comparable, and also I won't have the time to get into this. It is able now to put in new images into the curve last piece, this is sort of, earlier I mentioned weakly textured objects, loosely defined as objects for which what I just told you about, interest point-based methods just don't work because there are not enough interest points. Why do we bother? This is of high commercial interest. It would be really cool if my wife sees a handbag her girlfriend has, takes a picture of it, and then she wants to see where can I buy this handbag or where can I find similar ones. But so for unpackaged products, to use this unwieldy term, that's where weakly textured objects are unfortunately quite prevalent, and we can do those well yet. So the strategy here is too deep. We need to bring other features in, other than interest point-based features. So which ones would those be? Of course, edge-based features, contour-based features. Eventually, they will need to be joined by color features or material properties. I can recognize my MacBook when it's in cover on my messy desk. There's just a tiny part shining through, but because I can, so no contours, no interest points, nothing works. Even the colors are so distinctive, but I can recognize this distinctive surface properties. So the idea here is, and that's early days, we use segments. We do an over-segmentation of the image, create a hierarchy of segments by joining segments. Then each segment gets described by choreograms, which are all familiar. You are with those have been introduced by Toshev et al. It's basically, you have your the segment, then you take any 2 points, you will draw a vector between those, you record the length and angle of that vector, and then you also encode the surface normals of the edges at those contour points. And that you do for any pair, and you put this into histogram, that's essentially a choreograph. And then we do find non-accidental properties, as pointed out, so important. We don't represent, it's not a one-to-one where we just try to match or recognize, let's say, a Porsche Carrera by just having a single entry into the index. But we typically have 150 to 100 images per car or per object we would like to recognize. And then by matching the choreograms within this class and against other classes by standard methods, we can of course retain the most distinctive choreograms, and those are retained in the index. And here's the result on a car data set. So this identification rate against false positive rate, and sort of the green and the red are sort of the red is the Congas engine, still with the parallelized PD3 implementation that I had explained earlier. So this on its own is doing okay, but in absolute numbers not good enough. Then the choreograms on their own are the green ones. And again, the absolute numbers here are not that important yet, because it depends, of course, how many, it's actually normal. There are different ways to normalize this, but the take-home message here is, and not surprising, probably, that if you fuse the contour-based features with the interest point-based features for the false positive rate range that is relevant to us, let's say 1 in 100 images is sort of the rule of thumb we allow for goggles in this range. Fusing, integrating Congas with choreograms gives us about twice as much identification. And that was it. Thank you. And I can call this out. This is the last work in the weakly textured object that was done by Andrew Image, student of research design.
It's really exciting and really frustrating at the same time. I should just add parenthetically, I wish you guys would publish. It would be really beneficial to the people who work for you, and to the research community if you participated more by publishing.
Yeah, it's actually nice that you bring this up, because we just put down a paper, and Johannes Steffens, was working responsible for our face recognition channels. We put a very nice IEEE paper together explaining the face recognition systems that led to those amazing results. And it was sent in for the special issue IEEE real-world face recognition system. And we were invited to send it in, and the guys had the guts to decline it on the basis that it was not described to the level of detail that somebody could reproduce it. I mean, if that's the standard, and there's a lot of information in there, it's not like a we had problems to bring this out because, I mean, at some point there's some proprietary IP kernel down there that we don't want to necessarily divulge. But actually we are publishing, also Andrew submitted the paper on the deep detection. So we do this, but of course the community has to cut us a little bit of slack. That, I mean, many other academic papers are not fully reproducible either. But yeah, we're not shy, and when we join our group, it's often their first question when somebody comes from a good lab, hey, can I still publish? And the answer is absolutely yes. Because we value this exchange. I think typically there's more coming in by people giving comments on our work than we lose by, I mean, it's more the aggregate. I mean, the individual thoughts are not necessarily ingenious in every step.
So based on all this practical experience, what do you think are the fundamental problems that you'd like to see people working on in the academic vision community? Do you think we have to maybe past that? How long you think visual search over like the next 10 years?
Yeah, so I think if you could cover weakly textured objects, so Andrew right now is working this area pretty much by himself, and that's not enough. We need at least a small team of people. It's a very hard task, and actually we'll just be joined, or this next month, 2 more people joining, so there will be a small nucleus team of 3 people in this area. But this is a very hard challenge, and so 30, 50 people could work in this area, and we hope, of course, to see interesting work from academia that we could incorporate. Because I feel if we can do weakly textured, that goes a long way towards my 10-year prediction, that then we have most of the interesting objects in the back. So that's one area. We had earlier called out the photo OCR problem as something that bugs us a lot. Unfortunately, we have a very important team in place right now that makes good progress on that.
Sort of a pedestrian question. Does it take you a long time? How do you do the core wavelet, the feature extractions? Is that you're just looking at sort of interest points? How does that? It's like you have a lot of images to deal with, right? So
yes, so per image right now, let's say VGA image is about 150 milliseconds to extract the about 1,000 fungus features for that.
and there are 40 dimensions to the feature vector, or you have all.
Yeah, the raw one is still, I think there's a 45 scales times 8 orientations. I think the answer is pedestrian too. We have been using the raw wavelets for 10 years, and the code is super highly optimized. And that's why many people shy away from these features, because a SIFT is easier to code than a very fast fungus extractor. But you get nicely rewarded if you go through the if you bother to do.
Okay, so let's thank Hartmut again.